Good day, everyone. This is Ivan Escama speaking on behalf of my colleagues Alan Roberto and Professor Edwin Abucay. I'm here to talk to you about our big idea, building extraction and regularization through utilization of distributed computing for disaster risk reduction management and community resiliency. Alright, let's get started. Here's the problem. The Philippines is situated inside the Pacific Ring of Fire, which makes it vulnerable to natural disasters such as typhoons, tsunamis, volcanic eruptions, and earthquakes. Mapping of buildings is important in disaster risk management and hazard assessments. Disaster risk management plans often lack updated data on the location of infrastructure and residential areas. Local offices often store this information in tabular formats on paper without the spatial information. This leads to the lack of an integrative solution in harnessing various spatial data towards disaster risk reduction and management. Through the use of Geographic Information Systems, or GIS, we can map these buildings in a digital format and perform different analysis and processes to aid in disaster risk management. Mapping of buildings is usually done through digitization. Digitization is the painstaking process of drawing lines and polygons to represent various stuff like roads, administrative boundaries, and for our case, buildings. This process is quite tedious and time-consuming, and thus, the automation of such a task is important. Through the use of remote sensing technologies, specifically light detection and ranging, or LiDAR, building footprint extraction can be done with minimal user intervention. Remote sensing data such as LiDAR and satellite imageries are considered big data. Thus, it can be computationally expensive to run algorithms for building footprint extraction. And now, here is our proposed approach. We have developed a prototype of an algorithm for the automated extraction of building footprints in LiDAR datasets. The algorithm outputs an S3 shapefile of generated building footprints that can be visualized by most GIS. This algorithm is also capable of smartly utilizing a computer through the maximization of available resources whilst not interfering with its current usage. The primary inputs for the algorithm are LiDAR point clouds in the LAS file format, an open source format for storing LiDAR information. The LAS datasets can be requested from the DRRRM PhilLiDAR 1 program, the Philippines' flagship program in using LiDAR for disaster risk management. These LAS files are pre-processed using LASTools, a proprietary LiDAR processing software suite. The pre-processed data is then fed to the algorithm described earlier to produce the output shapefile. We are processing huge volumes of data, thus, the algorithm we developed can take a long time to run. Since we have an existing computer laboratory for our project, UPLB PhilLiDAR 1, we can fully utilize the laboratory through the use of distributed computing. Distributed computing is a computing model that makes networked computers, or nodes, share a common goal or finish a big task. Our laboratory has 10 HP Z230 tower workstations connected by a wired network. Our approach follows the master-slave paradigm where one computer sends units of work to other computers for processing. We have developed a prototype of the system BERTUD, which stands for Building Extraction and Regularization through Utilization of Distributed Computing, as our platform for distributed computing. BERTUD has a master program which provides an interface for sending work to other computers through the network. It also has a slave program run by other computers which in turn waits for the master program to send work, and as it receives work, it runs the algorithm mentioned earlier. Building extraction through BERTUD is efficient since workstations are not usually maximized by our project personnel. The algorithm that we developed can smartly maximize the usage of workstations without interfering with the personnel's work, since building footprint extraction is not the only task of our project. Building footprint extraction is not enough. We also need to associate other information like building use, the number of floors, building age, etc. in order to make sound observations and decisions for urban planning, hazard assessments, and disaster risk management. We can take advantage of available data from OpenStreetMap and GeoFabric. And we can also develop a mobile application for ground data collection as a form of crowdsourcing. Project personnel and local government units can use this application to collect information on the field for later use in building footprint attribution. So that sums up our approach. But how is it different from other existing approaches? Our algorithm can run by using only LiDAR information, whereas most of the other approaches use multiple remotely sensed imagery, which can be more costly. Second, we have two layers in the maximization of our computer laboratory, micro level and the macro level. In the micro level, our algorithm can maximize the available resources of a computer without interrupting its current user. The user is generating building footprints without him or her even knowing about it. And at the macro level, we developed BERTUD, a distributed computing platform for building footprint extraction that can send units of work to other computers through a wired network. The proposed project will utilize existing resources, i.e. the equipment and software of UPLB LiDAR 1. Other associated costs in the development and improvement are distributed as follows. Now, let us proceed to the demonstration of BERTUD's prototype. The prototype's backend was written using Python plus a handful of open-source third-party libraries. Its frontend was written using HTML, CSS, and JavaScript. Here, we have the master interface. On your left is the queue panel, where we can send work to the slave computers. And on the right, you can see the slaves panel. Currently, there is no slave computer connected. Now, let us try to connect a slave computer by starting the slave program. Let us go back to the master interface and voila! A slave computer has successfully connected. We can now see the CPU and RAM usage of the connected slave computer. Now, let us connect a few more slave computers. And we're done. Now, let us try sending work. Click on select LAS or LAZ files to be processed. Specify the directory of the input LAS files. Then click on the select output folder button and specify the destination folder for the outputs. When everything's okay, click on the plus button to add the files to the queue. The master interface will now send the queued files to the slave computers for processing. Once the slave program receives the input, it determines how much CPU power it can use to maximize processing while also giving leeway to the project personnel using the computer. When a slave computer finishes, it sends the output back to the master computer. We then run another program to produce S3 shape files from the slave computer's outputs. Here are some sample outputs. We overlay the shaped file to a digital surface model of an area in ArcGIS, one of the more popular geographic information systems. So that was our prototype, and we think that we can improve upon these aspects. First off, the output of the algorithm. It is far from perfect. There are still some misclassifications and errors in the generated building footprints. Second is the BERTUD user experience. We still plan to do a few tweaks on BERTUD's user interface to make it more usable to other potential users. We also have a prototype of a mobile application for field data collection for building footprint attribution. Currently, it can locate the user and store some data regarding the location, i.e. the type of building and flood events that happen in that area. In summary, mapping of buildings is important in disaster risk management and hazard assessments. Mapping of buildings is usually done through digitization, a painstaking process that can be automated by applying algorithms on remotely sensed data. We have developed a prototype of an algorithm for the automated extraction of building footprints in LiDAR datasets. We are processing huge volumes of data, thus the algorithm we developed can take a long time to run. We have developed a prototype of the system BERTUD as our platform for distributed computing to elicit micro and macro level maximization of our computer laboratory. So that's it for our pitch. We hope that you liked our idea and thank you for listening.